Hello everyone, and thank you for watching this video. And this video will focus on the organization algorithm I implemented in the EvoMass, which is called the SSIEA. So before we go into how to use this algorithm in the EvoMass, I will show you talk about a little bit about this algorithm. The algorithm is designed to support the explorative organization. So in the conventional organization algorithm is usually like this. They will only focus on one subspace in the desired solution space, and then will provide you a family of very similar solution. Of course, somebody used the algorithm like the NSGA2 and other model objective algorithm to make the organization algorithm, the result of the organization more diverse. But usually this come to another problem is that usually there are too many options, and you have to, and I see many researcher or people who use this have spent a lot of time to, to clustering and try to simplify the solution, and then to, okay, maybe they have 100 of solution in the Pareto form, and then to narrow down to 5 or sometimes even 1. But if you just only need the one, you just can run the single objective organization and to use like the Wasa function to search for the ultimate solution. So in the SSIEA, we use the island-based model to make the organization process can focus on different solutions space in the whole design space, and then to try to deliver the almost solution in different subspace in the solution space. So they can diversify the organization result, but also you can control how diverse the organization result, and and you don't need to do a lot of analyze and or to do a lot of extra or operation to clean up the organization result using the multi-objective algorithm. So if you are interested, you can check this paper. It's called SSIEA Hybrid Evolutionary Algorithm for Supporting Conceptual Architecture Design, or we'll also put the link on below this video. So let's talk about how you can use the SSIEA in the Rhino grasshopper environment. So in the Rhino grasshopper environment, here is already an organization workflow I established using the EvoMass and the Ladybug to calculate is supposed to be the solar irradiation on the surface of the building meshing. And you can find this case also in the for Rhino pages. So you can directly using this. And here have some context, the urban environments. And so we want to run the optimization to find the best solution that can maximize the solar irradiation in the winter, and also to minimize the solar irradiation in the summers. So I won't go into the detail of this setting, but because this video is focused on the SSIA, so we will directly go to the SSIA. But here I can show you some ideas how to make the fitness function, because the fitness function is how the SSIA know each of the design variant, the performance of each of the design variant generated during the optimization processes, and how to using the evolutionary operation like the crossover mutation to find the better solution during the evolutionary process. So in here you can see that here have different items in the fitness function, and usually I will consider the gross area of the building as one like the punishment function in the fitness function. So it's here, and here is I extract the area from the generated out components. So I also set an target area. So they will calculate the difference between the target area and the actual area of the generated desired variance. And then here is using a very simple one, just like to try to a little bit increase the performance by like the punished one have a large gap between the target area, between the actual area and the target area. But you can also have some other function. For example, you can use some like a sigmoid function to do this part of the punishment function, and and then you will. Here is the part that calculates the difference between the solar irradiation received by the building in the summers and the winters, and then you will multiply these two parts of the number to achieve the final fitness function. So when you use the EvoMass, and if the SSIEA is already integrated in the EvoMass tab, and you can find in here this one, the steady state island evolutionary algorithm. Once you drag this one into your canvas, for example, I delete this one, and they can automatically recognize the generated component in the EvoMass. So you can just drag this thing into the one. So you don't need to set the number of parameters when you use EvoMass, because they can automatically calculate the number of parameter based on the setting in your generated components. For example, if here I have 5 additive mass unit, and it means that they will have 13 parameter, because each unit will cause 6 parameter based on the X, Y, Z, the spatial location, and is the dimension, the free for the width, length, and height. And then if for the fitness, you can also drag this thing to the last output, or the outcome of the fitness function, and then you can finish the whole thing. And then you keep the here, and then you find this windows and the UI. Here is you can see how many variable in this thing is 13, because the first one is 0, and then you can click here the output. You can find here is the maximum. You can already check whether it's correct, because actually the SSIA also support 2 objectives. So for example, if you have another, you can also like here, you can click here, and then you can have a 2 objective, and you can define the optimization direction for each of the objective, because the value is how you to identify which objective is which component. For example, is 80.7274 should be this one, yeah, and the 66 and the 0810 should be this one, and then you will know which is the correct objective. But just move to the single objective one, and then you can define the direction. In this optimization, I want the difference between the solar irradiation received in the summer and the winter to be small, so I will try to minimize it. And then when you set up this one, you will go to the SSIEA tab, and here you will define some important parameter for the optimization. For the SSIA, the first one is the number of the subpopulation. So this means that how many subpopulation in here. Here have a 5 subpopulation. If you define 3, maybe just have a 3, and if you define 6, the optimization will become more explorative. So usually I will recommend to set like a 5, and the size of subpopulation means that how many individuals in each subpopulation. Usually I will, if you want the optimization run very fast, you can just keep the 15, but if you want to more accurate, usually 13 to 14 is acceptable. And be aware that you can see that how many iterations of the optimization if you calculate based on the current parameter setup. And here is a 350 iteration. It means that the optimization will be run 350 design generation and evaluation. And termination threshold is how many generations. This is similar to the evolutionary algorithm. Is how many generations you want to run. As a more generation, you will more have a correct solution. So if you make this to 100, you can see the iteration will become 2,150. And here another two servo function is that the ordinal Latin hypercube sampling. It means that you can click this one and to make the initial population more evenly separated in the design solution space, but this will to make you to this will consume a little more time to calculate the correct Latin hypercube sampling. And the second one is the k-means clustering. It means that they will cluster the whole solution, the individual in the initial population to each of the solutions subpopulation, because sometimes, for example, if all the individual is spread in this whole area, and you sometimes you want your each of the subpopulation is have individual close to each other. You will use this k-means clustering. And the mutation rate is here. If you set this the radiant decay to none, it means that will keep the stable mutation rate. But if you can change this, means that the mutation rate will be decreased during the optimization process, because when in the later stage of the optimization, usually you don't want the optimization too explorative, so you can just change a little bit close to the current normal solution. And the migration rate means that in sometimes some subpopulation is still evolving, so you can exchange some individual with other subpopulations. So here is you can define the mutation rate, but usually if you are making the migration rate too high, it means that the high performing solution from other subpopulation will overwhelm this subpopulation and this will decrease the diversity in the final optimization result. So usually you just keep this default is all right. And the last one is the tournament size. Usually it's 8 or 10 is okay. So if you hit the 10, it goes to like the 3,150. And after you all setting up of this, and you can run the optimization by just click the star. So here I will keep the star, and then the optimization will run automatically, I suppose. Yeah. So I won't run this optimization in here because there were two types of consuming. For example, usually it would take you 1 day or even several days. But usually I will recommend that you run a more faster simulation software to accelerate the whole optimization process. So let's cancel this one and close this window. Actually, when you finish the optimization, for example, here is the one I already finished. You will find a backup file. So you need to save the whole the grasshopper file in some places, and then the SSIEA component will automatically create this folder to record all the information during the optimization process. Here will be find the information in each of the generations. So I set 100 generation, you will find the 101. Because the first one is the initial generation. And then with this one, you can actually just directly extract the solution, or if sometimes the power down or your computer shut down, you can still retrieve or restart your organization by click the last one. So here we will just, for example, if you click the this one, they will have some time to recalculate. You can totally restart solving the organization during the, you can see that they only run the 300 iteration out of the expected 3,115 iterations. So let's, all right. So we will load the last generation. It will cost you more time because there are a lot of information and the whole data structure need to be construct during this process. So sometimes it will cost you like a minute to finish the reconstruction of the whole organization project. So just be a little patient. So if you're watching this video, you can skip a little bit to, because I'm waiting for the windows to pop up. All right, we see the final the whole tables of the organization result, and then usually I will click the only show the current population because you don't need the worst one in the early stage of the organization, and then show the fitness first, so you can see the fitness comes to these two here, and then you will click here to sort the whole list to make the best design variant, have the design variant with best fitness in the top of the list. And before going to analyze this solution, you will find some useful information in here. And here is the fitness progress trend line. You can see how each of the subpopulation evolve. You can find the purple one is run very fast, and then the other two, the other four is quite slow. And you can also see the information here. The information here means that this in the upper price means that the average fitness in each of the subpopulation, you can see that generally is still going up. So it seems that the whole organization is still reach the convergency. So if you run a little bit longer, you can get maybe more accurate solution. And the bottom part of this sticker lines means that the standard deviation of each of the subpopulation, it means that how difference of the individual in each subpopulation to each other in terms of with respect to their fitness. If if the standard deviation is high, it means that the individual in the subpopulation is quite different from each other. If it goes low, it means that the subpopulation is become the individual in the subpopulation is become similar with the organization process. And with the organization result, you can regenerate each of the design solution by right-click the mouse and then to generate the model. Yeah, this is the one. And let's see. And also you can generate another one. And if you are only looking to one subpopulation, you can also click here to only to show the solution in one population, in one subpopulation. And you can find that the one with red color is that the best solution in this current in this subpopulation. And of course, you can also filter to some solution. For example, you can only show the improvement solution. In this case, usually you need to show all the solution individual drawing optimization. You can find how to see all the improvement solution during the optimization. You can use to regenerate all these solutions to see how the solution evolve during the optimization process. And you can see the Pareto form is for the multi-objective algorithm, and also the improvement and in the Pareto. And all right, I guess, and also you can see the bottom line here is the generation, the current generation 101 means that it already finished, and then the 3150 out to the 300 150 means that all the iteration is finished. The migration means that 2 migration happened during the optimization, and the runtime is 2 hours and 30 minutes, because I running the solar irradiation is quite fast. And you can see here we also use the decay gradient, so you can see that the mutation rate is dropping from the 3.5 from the earliest 3.5 to gradually to the 0.35 to the 0.1 in the final iteration. So I guess this is the all about the SSIA components. So I hope I make this clear, and thank you for watching this video and using EvoMass. Thank you. Bye-bye.